Have you ever stopped to think about how we get something as simple as clean water, or pure medicine, or even the metal inside your phone? Well, it all comes down to a process that's so fundamental, it's practically invisible to us. It's the art of unmixing. Today, we're diving into the science of separation, what I like to call the invisible engine that powers our entire modern world.
So here's our roadmap. First, we're going to explore why separation is so incredibly important. Then we'll get into how to classify all the different kinds of mixtures out there. After that, we'll uncover the single, most powerful principle behind every separation technique. And finally, we'll open up the toolbox and see exactly how these methods create the pure substances that build the world around us.
You know, this quote really hits the nail on the head. Out there in nature, almost nothing exists in its pure form. It's all just a jumble. The air we breathe, the oceans, the rocks under our feet, they're all mixtures. And that means one of the biggest challenges we've ever faced has been figuring out how to take these messy, chaotic combinations and pull out the specific, useful parts we need.
Right, so this isn't just some abstract concept from a chemistry class. Unmixing things is a high-stakes, absolutely critical necessity that affects everything from our personal safety to the global economy.
When you get right down to it, there are 4 major reasons we have to do this. First up, removing contaminants. Think about picking stones out of rice before you cook it. It's about making things safe and making them work properly. Second, extracting resources. You know, pulling valuable metals from raw ore, that's the foundation of pretty much all manufacturing. Third, you've got scientific purity. In a research lab or a forensic investigation, even the tiniest bit of contamination can ruin everything. And last, but certainly not least, industrial utility. Isolating the active ingredient for a medicine, that's not just a process. It's literally a matter of life and death.
So where do you even start if you want to unmix something? Well, the very first step is to figure out exactly how it's mixed together in the first place. You have to classify the chaos before you can bring order to it.
Okay, so the first and most basic question you always have to ask is this thing homogeneous or heterogeneous? In a homogeneous mixture like salt dissolved in water, everything is blended so perfectly you can't see the individual parts. But in a heterogeneous mixture like sand and water, the components are totally obvious. Just answering that one question tells you which tools you can even think about using.
Now let's dig a little deeper and look at particle size, because this is huge. You've got 3 main types. Solutions, which have super tiny particles and are truly uniform. Suspensions, with big, clunky particles you can see that'll eventually settle to the bottom. And then there's the tricky one, colloids. Think of milk. It looks totally uniform, right? But its particles are just big enough to be considered heterogeneous. They won't settle out, but they will scatter light. That tiny difference in particle size changes the whole game.
So how do you tell them apart in the real world? Easy. You use the filtration test. If you can pour your mixture through a filter and something gets caught, congratulations, you've got a suspension. Its particles are big enough to get trapped. The smaller particles in solutions and colloids, nope, they'll slip light through. It's such a simple but incredibly powerful diagnostic tool.
Okay, now we get to the core strategy. Once you know what kind of mess you're dealing with, you need a plan of attack. And that plan is always built on one central idea: exploiting differences.
And this is it, the principle of difference. To pull any 2 things apart, you just have to find the one physical property where they're the most different from each other. Is one way heavier than the other? Is one magnetic and the other not? Does one boil at a way lower temperature? You find that biggest difference, and you use it as a lever to pry them apart. That's the key to doing it efficiently.
And these are the main levers we can pull. We can use differences in density, volatility, which is just how easily something evaporates, particle size, magnetism, boiling point, or even things like solubility and how well they stick to surfaces. Every single separation technique we're about to look at is just a really clever way of pulling one of these levers.
All right, time to open up the toolbox. Let's see how these principles get put into action, from the most basic, common sense methods to massive, powerful industrial processes.
We'll start with the classic, filtration. This technique is a direct application of that particle-sized lever we just talked about. The logic is beautifully simple. You put up a physical barrier that stops the bigger particles, but lets the smaller stuff pass right on through. So here's how it works. You pour your mixture through the filter. The solid stuff that gets trapped behind, that's called the residue. And the clear liquid that makes it through, that's the filtrate. It's exactly like making tea with a strainer. The tea leaves are your residue, and that delicious tea is your filtrate. Simple as that.
Okay, but what if you don't have a filter? Well, you can use nothing more than gravity to exploit a difference in density. This is a neat two-part trick that's perfect for separating a heavy solid that won't dissolve from a liquid.
This whole process just requires a little patience and a steady hand. First, you just let it sit. You let gravity do all the work. The denser particles, like sand and water, slowly settle to the bottom. That's sedimentation. Then, once it's all settled, you very carefully pour the clear liquid off the top. And that's decantation. No fancy gear required, just a solid understanding of density.
Now for something really cool. Let's see how a property as simple as magnetism can be scaled up to do some seriously heavy lifting on an industrial scale. The basic principle doesn't change, but the application becomes unbelievably powerful.
So on the left, you've got the basic idea we all learned in school, a magnet pulling iron filings out of sand. But on the right, that's the same idea, just supercharged into an industrial powerhouse. Crushed up ore gets dropped onto a conveyor belt that has a big magnetic roller at the end. As the belt goes around, the non-magnetic rock just falls straight down. But the valuable magnetic ore, it clings to that roller for just a split second longer, dropping it into a completely separate container. It's a brilliant, high-speed way to purify tons of material an hour.
But what if your components are perfectly dissolved into one uniform liquid? You can't filter that. That's when we have to get a little more sophisticated and turn to a technique like distillation, which cleverly exploits a difference in boiling point. You know, what makes distillation so elegant is that it's a closed-loop system. It's not just about boiling a liquid away, it's about catching it. First, you heat the mixture to turn the liquid you want into vapor. That's evaporation. Then, you capture that vapor and cool it down so it turns back into a pure liquid. That's condensation. You get your liquid back, but now it's completely pure.
Let's just trace the path here. We heat up the salt water. The water has a lower boiling point, so it turns into steam, leaving the salt behind. That pure water vapor then travels up and into this cool tube called the condenser. The second it hits that cool surface, it turns back into liquid water droplets, which then drip down into a clean flask. And just like that, you've literally made fresh water from the sea.
So, after looking at all these tools, let's just zoom back out for a second and appreciate the absolutely incredible impact that the science of separation has on every single part of our lives.
I mean, it is truly everywhere. It's in the filtration and sedimentation that gives us safe, clean drinking water. It's what makes sure our food is free of contaminants. It's the incredibly precise separation that makes life-saving medicines possible. It's how we get the raw metals from the earth to build our cities and our technology. From a crime lab to your kitchen, that invisible engine is always humming in the background.
When you really think about it, the ability to separate mixtures is the ability to create order from chaos. It's how we turn the raw, messy stuff of nature into the structured, pure materials that build our entire civilization. It kind of makes you wonder, doesn't it? What's the next great mixture out there that we need to figure out how to unmix?